Hello, thanks for joining us on yet another edition of Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley, your host. It is great to have your company. Coming up on today's show, we're going to be looking at a new way of exploring Mars. Now, we've been talking recently about helicopters. Well, they've got something else in mind, which is even more exciting, and it will get them into places they can't reach at the moment. And 10 years on, we are going to revisit the Higgs Boson. I've got one right there. See? Look, there it is.
Oh, there it is. There.
Yeah. And we'll be answering questions from Patrick, Paul and Talek about passing stars, constellations and asteroids. That's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as he does every week without fail, well, actually, he did fail this week. That's why we're running late. But anyway, it doesn't matter because it's a podcast for a lot of people and they can listen to it at their leisure, is Professor Fred Watson, astronomer at large. Hello, Fred.
Good morning, Andrew, or whatever time of day it is where you are. Thank you very much for that welcome. That's always a pleasure to be here, and looking forward to our chat this morning.
Yes, we've got a lot to cover, and it's going to be rather interesting, some of these things that have come up in the news of late. I've got to tell you, we've got a bit of an emergency in town today. We've been alerted by the local government that we have to boil our water for the next week.
Ooh.
Yes, a boil water alert. That's because of the flooding in the region. And some of those floodwaters have spread out over areas where cows go to the toilet and sheep and other animals. And apparently that's caused a problem with our water supply.
Oh, dear. Yeah.
So we're busily boiling water. Judy's done a rush down to the supermarket to see if she can get some bottled water. But I'd say by right now, every bottle of water in town is probably gone. But, that's our little situation this week. What's happening in your part of the world?
Well, you're absolutely right. There are places certainly not very far from us where the situation is quite dire. People who've got, water inundation in their houses, the rivers have broken their banks, the amount of rainfall that we've had over the past few days has been extraordinary. We've had more than a foot in 4 days. Foot of rain, 30 centimetres, and we're okay here in the bit of Sydney we live in because it's very hilly, and so the water just runs down the hills and ends up somewhere else. But certainly those people who've been, they've had inundation in their houses, and it's the third time this year. That's the absolute tragedy. They've just cleaned up from the last time, and sure enough, here it comes again.
Yeah, it's been horrible. I don't recall such a longitudinal wet period. Like it's been raining for a couple of years now, basically.
Yes, we've been in a lengthy La Nina event here in Australia, Eastern Australia, and it's not going away apparently. So,
well, apparently the La Nina is officially not in existence at the moment, but they've forecast it will come back.
Yeah, so I believe.
So yes, I did hear one report suggesting that we could be getting another 2 years worth of rain. It's And our local dam, which is 5 times bigger than Sydney Harbour, just 70 k's down the road from me, which supplies us, it jumped 20% in 3 days.
Wow.
I know. That's a lot of water. Extraordinary amount of water.
That's Burrendong Dam, isn't it?
Yeah, Burrendong, yeah.
It's a lovely spot.
Massive dam. It is huge. Yeah. Now, we best get down to business, Fred. Let's go to our first story. Now, we have been talking in recent times about the rovers on Mars doing their thing, trying to find evidence of past life on the planet, and the Ingenuity helicopter has been doing missions which have been proving very, very successful, but also helpful in the search for these pieces of evidence. But there are parts of Mars we cannot go, and there might be information in those places, and so they've come up with a new idea that might get us access to some of the atmospheric regions of the planet, which I find extremely exciting. I love this concept.
It's great, isn't it? I think so too. And
it's a giant ladder, way. It's a
Yeah, so this is a story out of principally the University of Arizona, their aerospace and mechanical engineering section. The reason we're talking about it is because of the publication of a paper in the journal Aerospace, whose title is, and gives the game away, Mars Exploration Using Sailplanes.
yes,
And the authors come from, as I said, Aerospace and Mechanical Engineering Department in University of Arizona and NASA Ames as well, Mountain View in California. So here's the lowdown. What we have with Ingenuity is, yes, a helicopter that has been taken to Mars by Perseverance, was expected to have 5 flights and, demonstrate that flying on Mars was possible. So far, we've had 29 flights,
yes,
which have been very, very successful. The thing is, Ingenuity, the device itself, has worked perfectly and demonstrated what an asset it is. You know, when you've got a rover on Mars, it's demonstrated how good it is to get just a few meters up into the air to look and see what's beyond the next rock or horizon or whatever. So Ingenuity is pretty basic. It's just got cameras on board. I think there are 2. And it's solar panels and its rotors and a bit of intelligence built into it because it has to fly autonomously. But what it can't do is take atmospheric samples. It can't sort of sense the temperature or any of those things. That's all done by Perseverance in this case. Yep. But the thinking behind the news story today is the atmosphere of Mars has a lot to tell us about the planet, the interaction between its surface geology and the atmosphere. And wouldn't it be great if you could get just a bit higher up, up to a few tens or maybe even a couple of thousand meters above the surface. That might be a bit ambitious. You might run out of air altogether up there. But that's what's led to this proposal to fly sailplanes in the atmosphere of Mars, gliders.
Yeah.
And there's a lovely image which is accompanying the article of actually the lead author of the paper, Adrian Buscella. He's an engineering doctoral student, and he and one of his professors is holding this beautiful, stunning sailplane with a long, slender wing, what we call a high aspect ratio wing, which is the kind of thing that I think they're envisaging that you might fly in the atmosphere of Mars, festooned with sensors, so that you can pick up all these bits of information about the composition of the atmosphere on Mars, about its pressure and temperature and all the other parameters, the humidity, which is very, very low. So that prospect of having gliders floating around Mars over the next couple of decades or so is really an exciting one. The question that arose in my mind pretty well straight away is how do you launch something like that?
Yeah, giant rubber band, I suppose.
Well, that's right. That's the standard technique. I remember flying gliders exactly with that, a giant rubber band to get it up into the air when I was a kid. And of course, a lot of gliding enthusiasts, they get a tow up from either a tow aircraft or a land-based winch, but don't have either of those on Mars for a robotic sailplane. So what they're thinking of doing, and it's in the abstract of the paper, it's basically it's summarised that the idea. Actually, I'm going to read directly from the abstract. The absence of a propulsion system allowing for a compact form factor means the sailplanes can be packaged into CubeSats and deployed as secondary payloads at relatively low cost, providing scientific data over locations inaccessible by current landers and rovers. Various sailplane deployment methods are considered, including rapid deployment during entry, descent, and landing of a Mars Science Laboratory class vehicle. That's one like Perseverance. And deployment using a blimp. There's another one.
Oh.
You have an airship to lift your sailplane up and send it away. And I should just mention, Andrew, the real crux of their argument here is that glider pilots know if you choose your flight path so that you maximize the ability to soar on thermals and things of that sort, you can actually end up going a very, very long way indeed, just with a glider, and sort of gaining energy gaining height as you go further and further. And the paper draws comparison between the way albatrosses fly, because that's what they do. They
glide. They just
glide.
And updrafts, and they can stay up for days.
Yeah, without one flap of the wings.
Yeah.
And that's good because the glider can't flap its wings. So what they say is, and again, quoting from the abstract, numerical results for complete dynamic soaring cycles demonstrated that the total sailplane energy at the end of a soaring cycle increases by 6.8 to 11%. In other words, if you do things right, you wind up, basically with more energy than you had to start with, and that really means height, I guess, in this context.
That's fantastic.
Yeah, it is fantastic. Yeah,
I suppose that means they'd be autonomous. They'd be kind of in the lap of the gods in many respects. So they'd be subject to the conditions that they faced at the time, but they would also be able to collect data and transmit it back to a base station of some kind, probably on a rover,
or maybe an orbiting spacecraft.
Yeah, maybe. Yeah. And then that gets transmitted back to Earth, and we can get almost real-time data about what's happening in the atmosphere of Mars. That's really exciting, because I read the article too, and basically it's an area we don't know much about. It's been untouchable. We've gone through it, but we haven't stopped to go, hey, this looks interesting. No, too late. So this is a way of actually getting up into those areas of the atmosphere that we generally pass through at speed.
Yes, that's right. It's that, you're on descent, coming down from orbit. And so that's right. It's an area of Mars's atmosphere that's, there's enough known about it to successfully use aerobraking for a spacecraft coming in from Earth. Yeah. That's good, but the details are certainly not known. I like the idea as well that these scientists have thought of this idea and developed it. They're actually preparing to do some experiments with sailplanes actually on Earth, but at much, much greater heights than you normally fly sailplanes, just so that you get the a sort of replica of Mars, the thinness of the atmosphere. That's right, up to 15,000 feet. Wow. That's 4.5 kilometers. So, that's where atmospheric conditions are most like the ones that you find on Mars.
Makes me wonder, though, if, like the helicopter, they had to redesign it for Mars atmosphere because it's so thin. They had to make the rotors rotate at much higher revolutions to achieve lift. Will they have to redesign gliders for Mars atmosphere compared to the way they would operate on Earth? And that, therein lies the tests at high altitude.
That's right. And I think you're right. I mean, from, the little I've seen of the imagery of this, it looks as though the kind of gliders that are being thought of have got really very high aspect ratio wings, very long and slender wings, almost actually mimicking the shape of the rotors on Ingenuity, which are, wider than normal helicopter rotors, but and have this long, slender shape to them. So, yes, my guess is that exactly as you said, the design of sailplanes for use on Mars will be quite different from what you would find here on Earth.
And I would imagine that they'd have a short mission life. How long would they stay up there?
Wow, how long does an albatross stay up there?
Good point.
So I think that the idea behind this is to give them quite a long life. It might not be infinitely long, but long enough to get good data and get that over a range of locations. So these things flying around Mars might give us much more information about the atmosphere.
Takes me back to school when I was in year 6, and a friend of mine, still a friend today, g'day Phil, he came into class one day with a secret new paper plane design. And we made a few of these, and he decided to test one in class with the teacher's back turned and gained altitude very quickly. It leveled off near the ceiling. Just as the teacher turned around, it went past the teacher's head, did a complete circumnavigation of the classroom, and then wait for it. I'm not kidding. This is true story. And then it turned back and landed on Phil's desk.
Oh, that's extraordinary.
Guess who got the cane?
Did he now? Yeah.
He did. Got the cane.
Oh, wow.
Yeah, he got caught by his own invention.
Dear me, yes, which came back and said, it was him.
Well, it's probably up there for a good 15 seconds, which, in a classroom scenario with a paper aeroplane is pretty impressive. I should give his name and number to NASA or the University of Arizona and see if he can help.
Right. Yeah, that's right.
I still make that design today for my grandchildren. They think it's amazing.
Okay, and it's different from the standard, is it?
Oh, much different, yes. Very boxy shaped thing. I could make one and show you right now if you like.
You'll have to show us.
I'll do it during the break.
All right, okay.
Yeah, all right. That's a good plan. But yes, so no timeline on when this might happen?
No, because it's going to depend on, fitting this sort of thing into a future mission. But it is interesting that they've considered how you get it to Mars, and they're basing it on the model of an MSL class, that's Mars Science Laboratory class of rover, which is Perseverance and Curiosity. They're both that. In fact, Curiosity wasn't known as Mars Science Laboratory for a while. So maybe, I think we're talking on a decade timescale, Andrew, but it's still so it's early days yet, but it is still very exciting.
Yeah, and not overly expensive by the sound of it, which is even
That's
better.
right. It would be, yes, it will be an inexpensive mission.
Yeah, maybe they can wait till we send people to Mars and they can just chuck it out the window on the way
with the rubber
down.
bands.
Yeah. Oh, well, hopefully we'll have more to talk about in this in the not too distant future. This is Space Nuts with Andrew Dunkley and Fred Watson. Sponsor. Let's take a little break from the show to tell you about our sponsor, NordVPN. Now, VPN stands for Virtual Private Network, and it's basically a way of insulating you against people who might want to get into your personal data. Nord is the best in the business. They've been at this for a long time. They know the trade. They are better than anybody. They also have the fastest servers in the VPN world. And they make your online data unreadable to others, whether that's hackers or maybe governments or whoever is trying to get your private information. Long story short, they protect your online activity. Now, as a Space Nuts listener, there is a special deal available to you to get hold of NordVPN. But right now, there's something else that you might want to take advantage of. It depends on which package you buy. There are certain security packages available through NordVPN. You can get the standard package, which gives you secure high-speed VPN, malware protection, and a tracker and ad blocker. But if you go up to the intermediate level, that's called the Plus standard, it gives you a couple of extras, including a cross-platform password manager and a data breach scanner. Or if you just want to spend a little bit more and get absolute security on a 2-year plan, the complete package also adds 1 terabyte of encrypted cloud storage. You get the lot. Now, as a Space Nuts listener, you can get that 2-year plan at a very low price. And all you have to do is log into the special URL that's been set up, nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. And then use the code SpaceNuts to get your discounted offer, no matter what level you choose. Check it all out on that special URL, and then just click on the grab the deal button to look at all the options available through the various plans with our sponsor, NordVPN. That's nordvpn.com/spacenuts, and use the code word SpaceNuts for a special discounted deal for you as a Space Nuts listener. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, it's been a bit of a celebration this week. I've certainly heard it mentioned in the news, and that is the 10th anniversary of the experiment that revealed the Higgs Boson. And it was sort of a red letter day in particle physics because it was something that was known in theory and had been known since the middle of last century. But then they basically pushed a button on the Large Hadron Collider and wham, bam, thank you, ma'am. Oh, look, it's a Higgs boson. What do we do with it now? Oh, hang on, I've dropped it. Where did it go? Let's sort of start at the very start and talk about what the Higgs boson actually is before we talk about the 10 years of research since.
Yeah. So takes its name from Peter Higgs, who is still a theoretical physicist, Professor Emeritus in the University of Edinburgh, and Nobel Prize winner for his work on this sort of thing. So back in the 1960s, Peter Higgs realized that our understanding of, what's called the standard model of particles, the fact that we think there are four fundamental forces that are understood by particle physics: the electromagnetic force, the strong and weak nuclear force, and gravity. Gravity, sadly, doesn't yet have a particle physics explanation for it, but those are the fundamental forces of nature. So he realized that there was something missing here, and that there must be. Here you get into the weirdness of quantum physics, Andrew.
Yeah.
There must be a field that permeates the universe, that's everywhere, some sort of field that is required to explain how those subatomic particles behave. And when you've got a field, you can also interpret that as being due to particles. So it's like, we think of, and we don't know what they are yet because we've never identified them, but gravitons as being the particles that are associated with a gravitational field. So he figured that there would be something called the Higgs field, naturally, after his name, and postulated that it would have an associated subatomic particle. And let's go and find it. So that was in the mid-1960s. And it took until, as we've mentioned, 2012 before it was found. I actually had the great opportunity of doing, it was a 60-minute segment that I did actually at the Large Hadron Collider in Switzerland the year before it was discovered. So it was all focused on the Big Bang and whether, there was this missing entity, the Higgs particle. And I remember we interviewed some physicists there, and but the question was, when do you think the Higgs particle is going to be found? As I said, this was the year before. It was, I think, September 2011. And one person said, within the next year. And the rest of the physicists all looked at him and said, really? No, you can't believe that. It's not nowhere near the next
Go
year.
back to paper planes, man.
Yeah. And sure enough, though, within a year it turned up. And so the key thing about the Higgs boson is that it's the particle that endows all the other particles with mass. Which leads to that classic joke, which I'm sure we've recited already on this show, Andrew, and I think you know what it is. Higgs boson goes into a church and the priest says, I'm sorry, we don't let Higgs bosons into this church. And the Higgs boson says, well, how do you have mass? That's the old Higgs boson joke. Yeah. It's a very nice one too. So anyway, the discovery, 4th of July was when it was announced in 2012. It's a discovery that was quite unequivocal. There's no doubt about it. That was the Higgs boson being found. And it's actually a nice little video clip, which I found on our favourite website, phys.org. But it's just, if you Google 10th anniversary of Higgs boson discovery, that'll take you to this 6-minute clip that really gives some lovely views of the announcement when it was made, because of course it was made to great fanfare with media, all sorts of media presence. But it was a result that came from 2 different detectors, Large Hadron Collider, which that's giant atom smasher sitting, straddling actually the boundary between France and Switzerland, not far from Geneva. That is the machine that was used to discover the Higgs boson and to verify the results beyond any doubt.
Of course, the big political argument that came out of it is which side of the border the boson actually manifested itself. So the French are saying, hang on, it was us, and you can't call it champagne.
Yeah, that's right. Yeah, exactly. Anyway, in fact, actually, I don't know whether you know this, Andrew, but the border kind of weaves through so it's a 27-kilometre long tunnel, a ring, underground, and it crosses the border several times. So I think it's
nature of the border.
Yeah, I think it's 4 times it goes across it. So, these particles, French, oh no, they're not the Swiss. Oh no, the French. Oh, no, sorry, Swiss. No.
It probably happened everywhere at the same time.
More or less. Actually, because these things are traveling at, now let me get this right. I think I can remember the number. It's 99.99998% of the speed of light.
Wow, that's pretty close.
It's pretty close, that's right. Yeah.
Do we know what it represents, though, the Higgs boson? Do we know what its function was?
Yes.
I mean, when it first was announced, some clever sub-editor or journalist somewhere referred to it as the God particle.
Yeah, that's right. In fact, actually, that goes back long before the announcement.
Does it?
People, yeah. I think that was, let me see if I can find a reference to that. I think that that expression was coined actually in 1993. There you are.
Oh, yeah.
It was in a book by Leon Lederman and Dick Teresi. They called it the God particle because the point they were making was the crucial role that the Higgs boson plays in our standard model of physics. And it is exactly what we've just said. It's how other particles acquire mass. And so the nature of the Higgs boson is crucial. And that is why 60 years of effort went into actually discovering it and finding it from the 1960s to 2012. The really interesting, it's really interesting the mechanism by which you observe the Higgs boson, because they, as you know, in the Large Hadron Collider, you wind up these protons to the speed I just mentioned, nearly the speed of light. You have two beams going in opposite directions, and at several places around the rim of the collider, you bring them together to collide. And it's the Atlas and compact muon solenoid experiments, which were where the Higgs boson was discovered. But so what happens is these things collide, but the Higgs boson is very elusive. For a start, for every billion collisions between protons, you only get one Higgs boson being created.
Wow.
And then decays stupendously quickly into other particles. So you don't really see the Higgs boson, you just see its consequences in terms of what it's decayed into.
Yeah.
And so it's by measuring what these particles are telling you that you can work out and confirm the existence of the Higgs boson itself.
Now, have they found any other subatomic particles in the 10 years since?
Yes, there have been others found, but not as fundamental as the Higgs boson. There are other new particles. And of course, work is continuing because, as you and I have discussed many times, our theory of fundamentals of nature is inadequate. Because for a start, we don't have a quantum theory of gravity. We know that gravity would have to have its quantum equivalents, the gravitons, but they've never been discovered. And things like, the astronomers provide one of the routes into trying to understand nature at its most fundamental, because we don't have an explanation yet for dark matter. We know that there's massive subatomic particles. We believe that is the most likely explanation, that there are massive subatomic particles which not seen in the colliders. And the Large Hadron Collider has been tuned up to look for something called supersymmetry, which is the idea that every subatomic particle has a kind of shadow particle, perhaps existing in a different dimension, which is supersymmetrical and more massive. And it's thought that possibly, if this supersymmetry theory is correct, maybe dark matter is one, or maybe even more than one species of these supersymmetric particles. The axion and the neutralino are the two that have been mentioned, even though we don't know that these things exist.
Yeah.
So a lot of the work of the LHC is looking for cracks in our understanding that would lead to exploring the possible new physics that might reveal where these other particles are lying. Actually, I have to say that supersymmetry has sort of gone off the boil a bit, because there's been no sign of it at all in anything that's done at the Large Hadron Collider. There are some little curiosities that are emerging from work done there and at other particle accelerators, which actually concern the weak nuclear force, the W and Z bosons, which carry the weak nuclear force. There's some little oddities that are showing up fairly consistently in the way they behave. And so I think that's sort of where things are going at the moment. Meanwhile, the Large Hadron Collider itself I think it's just started. In fact, it may even be today that they switch it on.
Yeah, I knew it was coming up.
Yeah, no, actually, it's a couple of days ago. What they call Run 3, which is something following a 3-year shutdown to upgrade its accelerator and its experiments. And that started a couple of days ago, will run till the end of 2025. Mm-hmm. And we'll get new collisions at a higher energy, 13.6 tera electron volts to be precise.
Wow. So are you anticipating another big breakthrough in the future from the Large Hadron Collider?
Really interesting question, because I go through my life thinking, something could pop out the woodwork any time. Yeah. And it might be to do with, as we were saying, these little oddities that are showing up with the weak nuclear force. So let's wait and see. What happens, I think, Andrew, is if something like, a big discovery like this is coming up, something equivalent to the Higgs, you start getting leaks of bits of information coming from the physics world. And sometimes that's picked up by the media, sometimes it's not. But those leaks often, a time when people start getting excited. It's a bit like the leaks that came up when we knew that there was going to be an image released a couple of months ago of the black hole center of our galaxy, Sagittarius A star. Yeah. There were media announcements put out, forewarnings that made it pretty clear what it was they were going to be talking about without actually mentioning it. A big discovery from the Event Horizon Telescope concerning the Milky Way galaxy. Well, that tells you exactly what it is, even though they weren't actually announcing that.
Yes, indeed.
And the same happens in physics as well.
Well, I often find, working in the media, that the newsworthiness of a story, like a particle being discovered by the Large Hadron Collider team, comes down to whether or not people will understand the story when it's published, because sometimes the complexity of a story kills it. Yeah. And unless they can simplify it into plain English, they sometimes just go, too hard, put it in the too hard basket. But, people with those sorts of interests can certainly read the scientific papers when they're published, which is probably the best way to go with it. It is like this.
Yeah, I wouldn't be able to understand a particle physics paper if I read it.
No. Well, I certainly couldn't. Yes. Yeah. All right, but more to come with the winding up of the Large Hadron Collider again as we speak. This is Space Nuts. Andrew Dunkley here with Fred Watson there.
Space Nuts.
Question time, Fred. This is where the audience sends us questions and we don't answer them very well. But we've got some really good ones today, and I think we'll just get straight into it because they're fairly self-explanatory. But there's a couple of them here that I don't think we've ever discussed before, particularly this first one from Patrick.
Hi, Fred and Andrew. This is Patrick from Centennial, Colorado in the United States. I have a question about stars that have and will pass through our solar system. I was reading an article recently about a star called Schultz star that they believe passed through the outer Oort cloud some 70,000 years ago. My question is, what are the chances that any Oort cloud objects that may have been perturbed by the passage of the star could be now heading into the inner solar system sometime in the future? Secondly, it's believed that Gliese 710 will pass roughly within 10,000 AU of the Sun in the future. With Gliese 710 being a much more massive star than Schultz's star, what are the chances that this passage could send Oort cloud objects or even Kuiper belt objects into the inner solar system? Thanks for taking my questions, and thanks for having the best astronomy podcast in the entire solar system. Have a great day.
Thank you, Patrick. Actually, it's the only podcast of its kind in the solar system, so yeah. But no, appreciate the support. I'm a bit confused by his question because I don't understand the concept of stars passing through our solar system. Does he mean solar system or galaxy or outside our solar system?
No, he means the solar system. But we're talking about, the solar system on its widest scale,
because so out way beyond the
way beyond the planets.
Yeah.
So we've got the Oort cloud there, which is probably something like 10, 15, maybe 20% of the distance to the nearest star. It's so big. We're talking about this shell of cometary nuclei, and that's the the dimensions of that, and the kind of distance that Schultz star is thought to have passed by are much, much bigger than the dimensions of the planetary system. So what's Neptune? 30 astronomical units, if I remember rightly. One astronomical unit being the distance between the Earth and the Sun, 150 million kilometres. So we're talking now about tens of thousands of astronomical units. So much, much further away, but still gravitationally bound to the Sun. So still, in a sense, part of the solar system. And it's a good point that Patrick raises. And you're quite right. We really haven't discussed this before. So Schultz's star, actually discovered by somebody I've certainly talked to rather than worked with, Alf Dieter Schultz of the Leibniz Institute for Astrophysik Potsdam, usually called the IAP, the Astrophysical Institute of Potsdam in Germany, not far from Berlin. Now, I've worked a lot there because the RAVE survey that I was involved with, looking at the speeds of stars, that was led from that exact institute. And so we went to many meetings and conferences there. And Alf Dieter is somebody I'm pretty sure I've spoken to in the past. So he found this star, which has, in fact, it's not just a star, it's a binary star. So there's a red dwarf, which is much smaller than the Sun, and a brown dwarf, which is smaller still, which are actually in the southern constellation of Monoceros, beg your pardon, the northern constellation of Monoceros, the unicorn, currently at a distance of about 20 light years. But it's the velocity of that star, its trajectory. When you track back, you see that it actually was in our vicinity quite recently in astronomical time, 70,000 years ago. The suggestion is that it passed within about 50,000 astronomical units of the Sun. And it's very close. That's sort of typical of the kind of distance that the Oort cloud is at. So Patrick's question is on the money, because if you tip something out of the Oort cloud, it takes something in the region of 100,000 years to get here.
Wow.
So something has been disturbed by the passage of Schultz's star, could be on its way. Fortunately, we might have 30,000 years before it gets here. But it's an excellent suggestion. There could be stuff incoming already that results from this close passage. And certainly
30,000 years to get here, 30 minutes before we realise it.
Yeah, that's right. Exactly.
Sometimes not that much.
No. Yeah, but certainly the thinking in terms of, the periodic bombardment that we've had over the Earth's history from comets and things. And this goes back to work with people who I did work with, actually, at the Royal Observatory in Edinburgh, Victor Clube and Bill Napier, who were among the first to suggest that Earth has been bombarded episodically by comets and probably asteroids as well. So when you do the analysis, you can see these periods of increased bombardment. It usually comes from cratering and records and things of that sort, and is interpreted as being the Oort cloud being disturbed by something like a passing star or a passing giant molecular cloud, which are the birthplaces of stars. So the material, all these things, the stars, the Sun and everything, go around the centre of our galaxy. It's sort of swirling around in their individial orbits around the centre of the galaxy.
Phil's paper plane could cause a disturbance in the Oort cloud.
Well, it certainly caused a disturbance on his backside, I think, from what
he got it on the hand. The cane.
He got it on the hand. When I got the cane, I got it on the backside.
No, broke his thumb.
Very so. Did it?
Yes.
Ooh, you couldn't get away with that these days.
Back then.
Oh my God, broke his thumb.
No, broke his thumb.
Oh
yep.
dear. Anyway. That's a
Patrick's
different
right,
story.
though, is what he's saying.
He is, yeah.
Right.
Yes, he's right. And actually, he also mentioned Gliese 710, which is another star which is expected to make a passage near the sun in a bit longer, one and a third million years down the track. But that's going to be even closer. It'll be about 10,000 astronomical units, and it's a much more massive star as well. It's not, a red dwarf or a brown dwarf. So that does suggest that perhaps in our very distant future there might be trouble ahead for our distant descendants because of inbound objects from the Oort cloud.
Fantastic. Not fantastic, but fantastic question. Thank you,
it's a
Patrick.
Fantastic question, yeah. It's bad news, but fantastic question.
and thanks for the vote of confidence. I'm going to do a bit of a switcheroo on the questions because sort of Patrick may well have answered Talek's question. Talek from Ireland has asked a question about asteroid danger. So I'm going to leap forward to that using the Higgs Boson method. And here we go.
Hi, Andrew and Fred. My name's Talek, listening from Dublin in Ireland. Heard your call for questions in episode 309, so I figured what the heck I'll ask. The worst thing that happens is it won't be answered. I was recently listening to episode 308 in the back garden, talking about 40% of asteroids not being identified when I saw a shooting star, which briefly burned brighter than a plane approaching Dublin Airport in the twilight sky. Episode 306 spoke about asteroid 7335 1989 JA, which was a relatively close approach in astronomical terms. I know the Earth moves at 30 seconds on its orbit and has removed many dangerous objects with historic impacts. Also, we're based on the surface of the moon. There's an estimate of 60 impact objects of about 5K or greater in the last 600 million years. The late Stephen Hawkins considered an asteroid impact to be the biggest threat to civilization. My question is this: does the scientific community expect that this historic average rate of impacts to continue in the long term? Or is the prevailing thinking we're on the downslope of a bell curve in terms of the likelihood of a large and potentially hazardous impact? Love the show. Found the podcast at the beginning of the COVID lockdowns in 2020. Been hooked since. Thanks a million.
Thank you, Talek. Great question. I think Patrick may have given him a hint as to where the future lies.
Well, that's right. Yeah. So, in fact, Patrick's right as well, though, because, when you think of asteroid impacts in particular, what you're seeing there is impacts by the debris that's left around from the formation of the solar system. This is just the
localized junk.
It's junk, and it's not spread evenly throughout the solar system, because we know Jupiter, being so massive, has sort of shepherded a lot of these asteroids into the asteroid belt, and there's also the outer asteroid belt, the Kuiper belt. But the bottom line is, what we're seeing is the last vestiges of planet formation, because planets are formed by things hitting one another and sticking together. And so in that sense, Talek is right. We're seeing, we're on the downward slope of a bell curve, because 4.6 billion, well, actually about 4 billion years ago, there was huge activity. Everything was crashing into everything else. It's what we call the late heavy bombardment. And then things gradually tailed off, and they're continuing to tail off, but not a level that we could ever measure, because it's over human timescales. It's the same as it was a million years ago. But then, exactly as Patrick's question alluded to, superimposed on that, things that sort of external influences, like the gravitational tug of a star passing close to the solar system, which can upset the apple cart, because you have still got this reservoir of stuff that hasn't been used. And actually, I think Patrick did suggest, or it's stuff that hasn't hit the Earth yet, if I can put it that way. Patrick suggested that if things got really bad, it could be Kuiper belt objects that are coming into the inner solar system and potentially dangerous, as well as comets. And that's a very good point as well. So, yes, two great questions, and well done for juxtaposing them there, because they're entirely interrelated. So what we've got is, what we've got is this gradual easing off of the planet formation process, but superimposed on that are bumps in the distribution caused by things going past the outer solar system,
like other stars.
Other stars.
Fascinating. And thanks, Talek. Lovely to hear from you, and hope things are well in Ireland. I played golf with an Irishman on Wednesday. He transferred from the army in the UK to the Australian Army, and he's now running the reserve here in Dubbo. Nice bloke too. Terrible golfer, but nice bloke. Now, to our final question, and this is one we haven't had before, from Paul.
G'day, Fred and Andrew. It's Paul here from Brisbane in Queensland, home of the mighty Maroons. I have a quick question about the way that constellations are represented on paper. The usual way to do it these days seems to be the geometrical pattern, the geometrical method, rather. And that's all great for serious astronomers and scientists, obviously. But they kind of make it a bit hard for me to visualise in the night sky. Picasso would have loved them, I'm sure. But, Fred, I remember you redrew a few of them in Space Warp, and they looked really cool. And back in the 1950s or 60s, H.A. Rey did a whole book called A New Way to See the Stars, where he drew all the constellations in a way that kind of, well, makes sense, so that, Virgo actually looks like a woman, and so on and so forth. I'm just wondering if we can't make his way of doing things, and yours, more of a standard thing for, school kids, ordinary people, that kind of thing, and leave the geometrical patterns for the more, how can I put it, scientifically inclined among us. Anyway, I hope you're all doing well. Certainly, that includes you, Hugh. Certainly hope you're doing better than me with this little bit of flu that I have. Cheers.
Thank you, Paul, and commiserations. Paul was referring to a football team, Queensland Maroons. Every year, for those overseas that don't know what he's talking about, every year the states of Queensland and New South Wales face off in a 3-match series called the State of Origin. And it's a rugby league game where our guys play against their guys, best of 3 wins the series. It's probably the pinnacle of the game. It's probably bigger than playing against other nations. The rivalry between New South Wales and Queensland is well documented. This all started back in the 80s. And New South Wales gave Queensland a real dust-up the other day to level the series at 1-1, and next week we play the decider. Unfortunately, we're playing in Brisbane, so I'm not putting money on the game. It'll be too close to call, but that's why I gave him a raspberry. Thanks, so Paul. Good to hear from you. Drawing constellations. You've done this, Fred.
Yes, I have. Yeah, that's right. Look, it's a great question, and actually, I'm indebted to Paul for drawing my attention to this book, which is one I didn't know about. I got a keen interest in old astronomy books. But yes, it's a book was called The Stars, A New Way to See Them, written by H.A. Rey, published in 1952, revised in 1962, and again updated in 1997. So it's had various editions, actually, and came about because of exactly what Paul was talking about. The author, H.A. Rey, was interested in astronomy, and he liked the stars and looked at them, but he found the constellations hard to remember because of the shapes that, as I've said, actually it says in Space Warp, most of them don't look like what they're supposed to be. These are the join the dot patterns that we're talking about. So he redrew them in a way that they are often portrayed today in the way that H.A. Rey redrew them. So something that just gives you a bit more of an insight, the lines between the stars that make more of a relevant shape for whatever these constellations are supposed to be. So that's great for star watchers. And yes, I did my bit in, improved constellations in Space Warp. But what Paul refers to as the geometrical descriptions of the constellations, what that means is the boundaries between constellations, which are delineated by almost legislation. It's the International Astronomical Union, which is the governing body of astronomy. And back in 1922, that was when those first of all, the constellations were kind of adopted formally rather than just being loose connections of stars. They were adopted formally in 1922, and the boundaries between them were drawn. And they usually follow lines of either right ascension or declination, which are the same as latitude and longitude on Earth. So it's kind of analogous to the way we refer to countries on the surface of the Earth. Like if you think of, a continent which is composed of many different countries, such as Europe, those countries have their boundaries. And as soon as you say something like it's in Germany or it's in Northern Ireland or wherever, you know what bit of the sky you're talking about. Sorry, what bit of the Earth you're talking about. And the same is true now with these constellation boundaries that the IAU put together. So if you say it's in Virgo or Leo or Gemini, then you know which bit of the sky exactly, precisely you're looking at, because they've got these boundaries between them, which are like, international boundaries. So from the technical point of view of the working professional astronomer, it's very important to have those geometrical boundaries. Even though they themselves are quite arbitrary, they just relate to our particular viewpoint from where we are in the galaxy and what stars we see. They don't have any physical meaning at all. They just help to define the area of sky that you're looking at. So, look, I'm a big fan of the idea behind The Stars, A New Way to See Them, H.A. Ray's book, because I think the more you can do to improve people's memories of what constellations look like, the better it is. And I see there's different editions. There's a children's edition, which was called Find the Constellations, which is still in print. So it's something that people can go out and have a look at. I'm going to start searching for a copy of the original book, though, if I can. The Stars, A New Way to See Them. I'll have a look on the web and see if I can find a copy.
Beauty. Thank you, Paul. And I wish you no luck at the football next week. Got a comment from Ollie on YouTube who says, I guess in fairness, there are apps these days like Stellarium that show the nice constellations artwork, if that's a way that you want to see it. And another comment saying that he uses a sky map. So there are other options.
Yes, that's right. Yeah. The apps are great, on your phone.
Oh, yeah.
I've got one. It's a freebie, so it's not the most sophisticated one, but I think it's Skyview I use. And
I think I use the same one.
Yeah, and it's great. Yeah. It's fantastic. Just such a novel use of the technology, of the fact that the phone's got accelerometers in it, so you know which way up it is and which way it's pointing. Yeah. And you've got GPS in it, so it knows exactly where on the planet you are. It's absolutely fantastic. Yeah.
Mm. All right. Thank you to everyone who sent in questions. We got a whole swag of them this week, so we'll work our way through those over the coming episodes. And thanks, Fred, for all your input. Really covered some amazing ground this week, so much appreciated. And looking forward to catching up with you next time.
Sounds great. Thanks, Andrew. Take care. Get rid of that COVID and we'll all be good.
Yeah. That's the plan. Fred Watson, astronomer at large. And just a reminder too, if you want to catch up with us online, you can do that through Facebook, where we have an official page, or the podcast group, which is a user-generated Facebook page. Just do a search for Space Nuts. You'll find them both. If you want to send us questions, do it via our website, spacenutspodcast.io or spacenutspodcast.com or spacenuts.io. There you are. And you can send us questions there. And don't forget to leave us some reviews, because reviews are very helpful to grow our audience. And you can also do reviews via Spotify now on Android devices, which you haven't been able to do in the past, but you can now. So there's another option for you. And if you want to look into becoming a patron, you can do that on our website as well. Well, that wraps it up. Just one more go with this paper plane, Fred, I think.
Absolutely.
See if I can get it to do a loop. Oh, no, it's stalled. That's it from us. Thanks for your company. We'll catch you again on the next edition of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.
See if I can remember how to make one of these things.
Oh, yeah, that'd be great.
Take a standard piece of A4 paper.
Indeed.
And you take it across the top, a fold like that.
Oh, right. Yeah.
Then you open that, and then you cross it over on the other side. Some people will probably be aware of this design, because I think it's been around a while now.
Yeah.
So you basically do that the other way. Yeah. And then you've got these creases, and you fold them in to square off the nose, or point the nose, right?
Yep.
Which won't stay pointy. So you end up with that, right?
Yes.
Then you fold up the edges.
Ah, that's right, yeah.
Like so.
And you do it again, don't you?
No, that's how you make that magic box thing.
All right.
Then you just fold it all in. It sort of gives it a bit of bulk at the front.
That's right, to give you the
and then you
the
fold back the point to square off the nose, which I know doesn't sound aerodynamically brilliant, but so you end up with that.
Yeah.
This is a very rudimentary effort because I'm doing it without much precisions. But then you fold it up like that. You fold down the wings, 1, 2, and then you fold up the wing tips just to give it a bit of trim.
Mm-hmm.
And you end up with that kind of look.
Look at that. Ooh, yeah.
And then
snazzy.
it needs a tail. And if you want to put trim tabs on it or
elevators and ailerons.
You can do that. I never bother. And that's it. So that's what he flew.
Yeah.
That's what he flew around the classroom. And they usually, I'll try and fly it to the back of the room. They usually fly really well.
Yeah, pretty good. Bit nose heavy there, but
I probably needed more velocity.
Yeah,
because they do like to be chucked, those ones. But my grandchildren love them. Every time they come up, make me a plane, make me a plane.
Very good.
Yeah, see a little bit of bonus footage for our live viewers.
Exactly.
If you want me to draw the design and send it to you, no, not going to happen.
No,
I wouldn't know how to do that.
Just replay the YouTube and you'll find out how to do it.
Well, I'm not sure I demonstrated it very well.